Okay, in this video, we want to talk about the table that we have for design generators. So far, we said that, okay, so we have like the, we are going to decide on our design generators, and then we are going to find out our, they are going to defining our relation, like I is equal to something, and then we are going to find out our aliases, right? So let's see how can we find out, how can we decide on the best or the optimum design generator for each case that we would have. This table that you see on page 28 of the notes is talking about the number of the runs that you would have and the number of the variables. So here the number of the variables is that, in fact, the number of factors that you would have. Here is the number of the runs. For example, if I have, like, let's say I have 7 factor and 8 number of runs, then this is going to be my design generator. So I would have all of these ones as my design generators. But when you are working on that, you can write down, instead of this plus and positive and negative number, like sign here, you can write down D is equal to positive and negative, like AB is the same, right? And for example, let's read this one. See how we can read it. So here we have the 2 power 7, like 2 by 7 as my full factorial, right? And then, because we want to have, we just have 8 runs, so it would be -4. So in fact, in the denominator, we have 2 power 4, right? And that's my fraction. And then this 3, it's going to be my resolution. So this 3 that you see here, it's going to be our resolution. And here we have D is equal to AB, E is equal to AC, F equal to VC, and G is equal to ABC. So these are my design generators. So defining relation, when you want to do that, it's going to be like I is equal to ABD, equal to ACE. I'm just multiplying both sides by the factor that I have here. BCF and ABCG, and then I'm going to multiply these ones to get more. But the smallest number of letters that I would have, the smallest word that I would have in my defining relation, it's going to have 3 letters. So I would say that the resolution is 3. You can work on that, like any of this. You would say, let's say I have 9 factors, and the number of the runs that I have is 32. Then I can write down like here, so it's going to be 2 power 9, it would be your full factorial, but 2 power 9 minus 4 is going to be my fractional factorial, and then the resolution that I have is going to be 4 here. So from left to right, when we go, as you see, the number of the resolution is going to increase, which is a better thing. So we want to have the higher, like, number of the resolution when we are working on our designs. Okay, so here is an example. Look at here. I have 32 runs, and I have 1, 2, 3, 4, 5 factors. And the factors is written here, like on the bottom of the table, like A, B, C, D, E. That each of them, like, there are different factors, like variables that we have. So the first thing that we can do is that we would go to the table that we have, and I would say that, okay, I have 5 runs. One thing that I can suggest is that if you print there are a few tables that if you print in this course, it's going to be very helpful for you. One is the design generator one from this chapter, and the other one is the screening design table that we would have it later. But I have the printed version of the table of the design generators. Then I'm going to look at it. I would say that, okay, the number of the variables is 5, and the number of the run that I have is 32. So 2 power 5 is going to be the optimum design that I would have, like based on this table. Here we want to work on it as like we want to work to see that if we had like with the 2 power 5, what would be, how can we find out the confounding pattern and those ones. these stars that you see here, later we are going to talk about these stars like in few slides. So I have these ones, and then I have, these are the response, the negative, positive of that. These are different runs. So based on the runs that we had, so we would decide on the negative and positive of them. And then we'll estimate the effects. Look at here, I have A, B, C, D, E, the effects of them. This is the average, like that would help us find out beta null. And then I would have A, B, A, C, A, D, like their second order interaction, third order interaction, fourth order, and the fifth order interaction that I would have. So we're going to find out all of these effects based on the equation that we had before. So we said that effect is going to be positive minus negative, or contrast divided by divisor. For contrast, we said that, okay, so you're just going to have like sigma Li by I, right? They had in chapter 6. And for the divisor, the equation that they had was that R times 2 power k minus 1. And k was the number of factor, R is the number of the replication. So here we don't have any replication, so R is equal to 1. So just consider this. If we had like the partially replication, like the example we had in chapter 6, or we had the center points as replication, but there were center points for it. And you can find it in tutorial 8 that when we have the center points of it as a replication, we consider R is equal to 1. And then with these ones, we can find out the sum of the squares. When we find out the effects, we're going to find out the sum of the square. And for the sum of the square, we said that is equal to R, 2 power k minus 2, and then effect square. So we found that the effects here. So we can find out the sum of the square, and then we can develop our ANOVA table, right? Let's look at here. In the previous chapter, we said that we can show it by ANOVA table, or we can have normal priority plot. So this is the normal priority plot. We have the expected value, and then we would have the contrast. Here you can have contrast, or you can have the effect as well. So when we have the normal priority plot, here is the normal priority plot for the full 2 power 5 factorial. We are going to draw all of the, like all of these effects that we find out. We are going to have it here. And then you will see that in your normal priority plot, the ones that they are, we said that the ones that they are on the same line, those are not significant, but the ones that they are far away from the trend, so there would be a significant effect. So here, D, E, E, B, D, D, and B, there are significant terms. Even when you look at here, you can say that, or at least you can separate them from the rest of it. And in ANOVA table, we will see that. We can get the same result from ANOVA as well. So we have these ones as significant one. There is something very interesting. We can also estimate the error variance from the non-significant effect. So the equation that we have is that we would say the estimate for S2 is going to be the variance of the effect of non-significant term that we would have, times 2 power k minus 2, k is the number of the factors, and then the variance of the effect of the non-significant. When we're going to find it, we would use this equation for it. And this k is we would have the k degree of freedom. So this is just one way of finding out the error variance. We have different, like we could have a replication and we can get the pure error, find out the pure error from the replication, and then we say that if there is no lack of fit error, so we would say our error of the variance is equal to the pure error, like the ones that we had in chapter 6. Or we can have center points, we can find out again the pure error and the variance of the error, or we would pull the variance, right? Or we can have like partially replication, and we can find out the error variance. Or here, when we have the significant and non-significant one, from the non-significant one, we can find out the pure, like the error variance of it. So let's look at here. This is the analysis of runs marked with the star. So the ones that we had at on the first, like when we were on this page. Oh, sorry, I have to go back. So here is the table of the example, right? So all of these stars, it's like that, let's say we have 2 blocks. Or we just decided to have these like star runs as runs. We divided them. And then when we looking at them, it's like that, all of those ones with the ones that they have a star. So I would write down the runs like this, and then I would estimate the effects, like the average, and then the effect of A, B, C, D, E, and the effect of whatever interactions that is gonna come with it, like with these star ones. I would find out the interactions of them as well. And then I get the betas, but we want to see that are these reliable or not. So can we rely? Can we say that we are going to get the same result? What can we do is that, again, we can have our normal probability plot for it, right? So let's look at the normal probability plot of it. It has shifted a little, but again, so D, E, E, D, B, D, and B, they're the significant term. So it gave us the same significant terms, even we are working with the fractional one. It's a half fraction of the 2 power 5 factorial. So what do we say? We can say the answer is that yes, we get the very reliable results when we compare it with the full factorial ones. So now let's become a bit more formal. How was the half fraction generated? So we said that like the same methods that we had before. So we say E is equal to the highest order of interaction, A, B, C, D, as design generator. So I is going to be A, B, C, D, E as defining relation. What is the D interaction compounded with? So you're going to multiply D by the defining relation, right? And you would say, you find out DE is compounded with the ABC. What the estimate of the D interaction really present. So when we have the D interaction equal to minus 9.5, the question is that, so what does it really represent? Okay, so to answer this, that what does the estimate of DE interaction really represent, what I would need to write down is that I need to write down the here, that the compounding, I'm gonna write it down here and then I will share, like make this one bigger on your, in our recorded video. So I would say the DE, the confounding of DE, when we look at it, is DE plus ABC. So it's going to be DE plus ABC. So in fact, when you look at it, let me just share my. So what's happened is that this DE is from fraction, right? So this is the value that we want to find out for fraction. And this one, DE and ABC, they're confounding. It's like that we tried to find out, we said that, okay, so that was my full fraction, and then half of, like, this is the half of it that goes to the principal, like the principal fraction that I would have. So I would use DE or ABC. So I can say these two, the value, they comes from the full factorial. So I would say here, these two are coming from the full factorial. So here, the value of DE is going to be equal to the. Go back and look at the, on a slide, what's the slide number, 30. like then not the 31, like 28. Try to read the effect of D and ABC, and then compare it with the ones that you would get for the from the fraction one, the half factorial one, half fraction factorial. So here for the DE, when I look at it, DE, it's going to be minus 11. It's at the bottom of the slide 28, isn't it? So it's minus 11 plus the ABC. When I look at it, ABC, it's 1.5. So 1.5. As I said, these two, we're gonna read it when we have the full fraction. And this one is for the like full factorial, sorry. So this one is going to be for the half of the fraction that we have. So minus 11 plus 1.5 is going to be minus 9.5, right? Now, minus 9.5, go back to the slide number 30 and read the value for the DE. You can see that the value, the effect for the D is 9.5, minus 9.5. So in fact, if I go back to the slide, when we have this question that was, what does the estimate of the D interaction of the minus 9.5 in the like fraction one really represent? It really represent the combination of the DE and its confounding pattern, right, in the full factorial. So in the full factorial, we had like D plus ABC, right? So these two, they were confounding. If you add them, the value of them, you add them, it's going to give you the value that you would get for the fraction. So that's the meaning of it. The next one is that what defining relation would give the unmarked, like the trial? This is a complementary fraction, right? So you would say E is equal to minus ABCD and I is equal to minus, like you would add the negative sign for it. And the next one is the what is the resolution of this design? So we would say the resolution is 5, since there is 5 words in the defining relation. So when you look at it, it's like that. We would say, we said that E is equal to ABCD. So I is equal to ABCDE, right? Oh, it's written here. So we would have like the smallest number of letters that we have in the words of the defining relation is 5. So we would say this is the resolution number here is 5. Here is 5 words, it's like 5 letters in the words that we would have. Okay, so combining the two half fraction yields unconfounded result. So fraction 1 was that I equal to ABCDE. Fraction 2 was I equal to minus ABCDE. So let's say the estimate of the DE interaction from fraction 1, and this is the one that I just wrote down on the board, but it's like on the another part of it. And then let's have the estimate of the DE interaction from fraction number 2. So here we have minus 9.5. The estimate of the fraction for the fraction number 2 is minus 12.5. Because this one is DE plus ABC, but when we have fraction number 2, is the principal fraction. In the alternate fraction, we would have DE minus ABC, sorry. So the value of it is going to be minus 12.5. So then if we get the average of it, average of the DE and for the fraction number 1 and the fraction number 2 is going to be minus 11, and the average of the LDE minus, like the ones that we have for the fraction number 2, is going to be 1.5. So this minus 11 is going to give you the DE, and this one 1.5 is ABC. So what are we doing here is that we are just playing with it a little, like in different ways that you can find out like the effects that you would have for D and the ABC. We can resolve compounding to a judicious choice of the fractions. Running another fraction and combining may decouple, de-alias some of the confounding effects. So it's not that, we don't say that we are hoping to have like more fractions all the time. Sometimes it's good, sometimes it's not good. Depends on the situation that we have. This is another example. Like, no, this is the same example that they have for the 5 factors. Oh, but we have it like in 8 runs. So we had the 5 factors in 32 runs, and then we divided by 2. And now here is that we want to divide it like we would have 8 runs. The following 5 factors are to be studied at 2 levels to determine their effect on melt temperature. We can only use, let's say, 8-run design. What should we use for design generator? What would be your answer? You can pause the video and answer this and then come back and compare it with our answer. So what are we going to do is that we are going to go to our table of designs, like design generators that we had, and then we have 8 runs and 5 factors. So we have 5 factors, and then we would have 8 runs. Let me just show it to you like this. Okay, so look at here. We have the same table. I was just looking to see that what did I write down here. Sometimes you write something and you're embarrassed to show to anyone. It's like that. It's like hints, but these are good. So let's say here I have the number of the factors. So I have 5 factors, and then the number of the runs is 8, right? So this is going to be like the optimum design that you could have. If it's not very clear in this, like while I'm recording that, you can go on I believe on page 27 on the notes, and then you can find it by yourself. So here is like 2 power 5 minus 2 means that we would have 2 design generators, right? And they're with the resolution 3, so you can see 3 here. And the design generator is there that D is equal to AB and E is equal to AC. So to answer that, what should we use for design generators, you would say, we should, if I ask you in the quiz, you would just look at this table of designs and simply you would say, okay, so D is equal to AB and E is equal to AC. This is going to be our design generators. Let's go back to the notes. So this is kind of how we would use for the design generators. Then when we say D is equal to AB is equal to AC, we are going to find out I. So, and then for, it's like that, you would say, you would multiply both sides by D, and you would multiply here by E, and then you would multiply those together. So it's going to be like ECDE, ABD, and ACE. Then you can write down the compounding pattern. So you have all the compounding pattern here. Choose one of them and practice. So what is the design resolution based on the table? Based on that table that we had, you can say it's 3, or even here you can look at it. Look at these words that you would have. The letters, the minimum number of letters that we have in words is 3. So the design resolution is 3. How many terms are there in the model? So how many terms do we have? So we have 7 parameters, right? And we have 1 term for beta null. So we would have 8. If you want to write down the model, what are you going to write down? You would say beta null, and then you would say beta 1A or ABCDE or BD or CE, right? Plus beta 2B or CDE or AD or ABCE is like the compounding patterns that you would have. And you would write it down until like you would reach BE, and then plus error. So that's going to be your model. You can write down the model by yourself, and then let me know if you had any question about it. So here we would have the, so we have 5 factors in 8 runs, and here is the melt temperature. These are the treatment combination that we consider, and we would say that the main effect of A. So we are going to calculate the main effect of each of them, right? Just can say, let's find out the contrast and then divide it by divisor, or you can say the positive one, the average of the positive one minus the average of the negative one. Both is going to give you the same answer. As an example, please calculate the main effect of factor B. I don't write it down on the board because we did it many times. So you have the factor B, you have the positive one and negative one. The final answer of that one, it should be 5.95. like the main effect of B. This should be 5.95. When you do that, just check your final answer. And the effect of the AB interaction, the final answer, it should be 0.1. But what are you going to do is that you're going to have another column here, A times B, and then negative and positive, and then just get the average of the positive one minus the average of the negative one. Or you can say the contrast divided by the divisor, and you can find it. Now, let's look at our ANOVA table. Here is the effect and interaction. We keep up to 2 factors only. Most of the time, we remove the 3rd factor and 4th factor interactions. Finding them through the, like, to think about it, you want to consider like 3rd factor interaction is like that you're considering 3, you want to control 3 factors at the same time. It's not easy in the lab to do that. Because of that, you're going to try to keep the like 1st and 2nd interaction. So it's like you just wrote down the main one and the confounding one. Their effects are the same, right? When the effects are the same, sum of the squares are going to be the same. Degree of freedom that you would have for them is going to be 1 for each of them. And then we're going to find out the error with the same equation that we had. So we'll say sum of the square of effect is going to be R 2 power k minus 2, effect power 2. So here, it's just one more thing. Or it's going to be the amount of the complete replication of the full design, or it's going to be the fraction that we would have here R. Because in this chapter, we just learned about the fraction, right? And then we would have the degree of freedom, like the same thing that we had before. K is the number of factors. Error, we can estimate the error terms from replicates. And then we would use it in the, we would say mean square of each of them divided by the mean square of error. And to find out F observed, we would compare it with the F from the table. And then we're going to find out which terms are significant, which terms are not. What you can do here, you can plot the normal priority plot as well. But just be cautious, you just have 8 points. You have 8 runs. So probably finding out based on the normal priority plot is not going to be as clear as this one. Another thing is that when you look at this effect on sum of the squares here, we round off the numbers. Here we just did it. And the equation that we had, it was the same. So when we find out, when we find out the value of the mean square and mean square error, then we can find out which ones are significant, and as I said, which ones are not. Okay, so in the next video, we're going to learn about the screening, like how we deal with the screening design, which is it's a little different than these design generators that we had.